Hello students, let us start our today's session from the chapter Aldehydes, Ketones and Carboxylic acids. Today we are going to discuss about the acidic nature of carboxylic acids. Along with that, we have little more topics about the derivatives of carboxylic acid. That too we will discuss today. Okay, let us start the acidic nature of carboxylic acids. So we know well, acids are the substances that can able to donate the proton. So how far they are capable of releasing the proton, that much they are said to be a strong acid. So in this case, we are going to discuss about the acidic nature of carboxylic acids only. But these carboxylic acids are weak acids compared to mineral acids. What are called mineral acids? Hydrochloric acid, sulfuric acid, nitric acid, phosphoric acid, etc. So these acids are mineral acid, but those are said to be a strong acid. Compared to mineral acid, carboxylic acids are weaker acids, and here when this carboxylic acid is treated with water, see, water it gets protonated and carboxylic group that becomes a carboxylate ion. So the lone pair of electron on oxygen atom of water molecule that abstract the proton from the carboxylic group. So we are getting hydronium ion. So as there is a removal of proton from the oxygen, oxygen takes the negative charge because the bond is like that. From this oxygen take away the electrons. So we are getting carboxylate ion. This carboxylate ion further undergoes resonance stabilization, and hence the negative charge on oxygen atom that can move over the another oxygen atom. So we are getting the delocalization of negative charges between the two oxygen atom of carboxylic group. So as these negative charges delocalized between oxygen carbon oxygen or oxygen carbon oxygen, so we can make these negative charges are delocalized among these three atoms. So it can be represented with a half circle with the negative charge. Okay, let us write the equilibrium constant for this reaction. Equilibrium constant is, that is nothing but the product of concentration of products divided by the product of concentration of reactant. So here the products are hydronium ion and the carboxylate ion. Those concentration terms are taken, which is divided by the concentration of carboxylic acid with the concentration of water. And here the carboxylic acid dissociation is favored only in large amount of water. When you increase the volume of water, the dissociation of carboxylic acid will be more favored. And hence, when you compare the concentration of water with the carboxylic acid, we can say the change in concentration of water may negligible. So this you can consider change in concentration of water remains constant compared to the change in concentration of carboxylic acid, and hence this concentration of water can be multiplied with the equilibrium constant. So equilibrium constant is one of the constant, and the water concentration is also remains constant, and hence the product of both constant, it becomes equal to another constant. It is said to be dissociation constant of acid. So Ka equal to the product of equilibrium constant into water equal to the product of hydronium ion and carboxylate ions concentration divided by concentration of carboxylic acid. Now for this Ka, we can find out what is the pKa of the acid. We know pH of acid is given by minus log base 10 H plus ion concentration. This is what the formula for pH of the acid. Here we have taken the dissociation constant of an acid. That's why Ka that can be written minus log base 10 Ka. Instead of hydrogen, we are taking the dissociation constant Ka. So pKa equal to minus log base 10 Ka. or pKa equal to the minus sign that can be taken to the power of the Ka, so we can write minus 1 here. To apply the reciprocal of this one, we can have pKa equal to 1 by log based on Ka. So how it seems? pKa inversely proportional to dissociation constant. So pKa is inversely proportional to dissociation constant. So from which we can identify smaller the pKa, stronger the acid. This is we should know. So when pKa value is smaller, then the acid is said to be a stronger acid. So for example, the strongest acids are always considered whose values are less than 1. So when we compare the pKa values of some of the carboxylic acid, we may find the trifluoroacetic acid has 0.23 value. See, this value is less than 1. So in the carboxylic acid, the trifluoroacetic acid is found to be much stronger, just like that of mineral acid, and the benzoic acid is found to be 4.13 and acetic acid is found to be 4.76. So this is what the pKa values of some of the carboxylic acid. Okay, let us consider now how these carboxylic acid values are greater or smaller with that of mineral acid. Already we discussed mineral acids are stronger acid than what is that carboxylic acid. Then how trifluoroacetic acid only it becomes the strongest acid? Because the 3 fluorine atom present in trifluoroacetic acid is most electronegative atom and it is present thrice the time. So that accumulates the most electronegative values of the entire substituent and hence the withdrawal of electron from the OH group becomes much higher and hence the hydrogen that can be easily donated. Similarly, these mineral acids are used to dissociate completely at all concentration. Here we said the dissociation of carboxylic acid increases when the water increases, dilution increases even we can say. But in the case of mineral acid, even a small amount of water is present, the mineral acid will dissociate completely. So mineral acids are stronger acid because they can undergo complete dissociation at all concentration. This is one of the reason we can say why mineral acids are stronger than carboxylic acids. And carboxylic acids acidic nature is influenced by their substituent, but mineral acid they themselves have their strong nature. Now let us compare the acidic nature of carboxylic acids with phenol. And I said already mineral acids are much stronger than carboxylic acid. At the same time, when we compare the acidic nature of carboxylic acids with alcohols or even with phenol, it is found to be alcohols are much weaker acids than water. Since when we discuss about the acidic property of alcohol, we said alcohol able to accept the proton from the water. So they are said to be Bronsted bases. But in this case, carboxylic acid able to donate the proton. So here water accept the proton and hence water is said to be a base but carboxylic acid is said to be an acid. So from that correlation itself we can identify alcohols are weaker acids compared to carboxylic acids. Now let us compare the acidic nature of carboxylic acids with the phenol. So phenol versus carboxylic acid. We know well phenol upon losing the proton, because phenol is also able to lose the proton with strong electropositive metal or with the sodium hydroxide, we will get sodium phenoxide ion. So here I have taken only the phenoxide ion. In this case, let us write the resonating structures of phenoxide ion. This oxygen, it has negative charge, but the electron density of the benzene ring is much greater, so it is more electronegative than oxygen, and hence this ring, it withdraws the electron. Subsequently, the electron from the first position comes out to the second position. So see that here oxygen possesses the positive charge, carbon possesses the negative charge, and the negative charge enters into the ring and the other pi bond that comes to fourth position. So we are getting the negative charge at fourth position, and later on this negative charge goes into the ring and the next pi electron that goes to the sixth position. So this is also we are getting. Finally what happens? This negative charge enter into the ring and oxygen withdraws its electron. We are getting phenoxide ion. This is what resonating structures of phenoxide ion. Now you compare this resonating structure with that of carboxylic acid. In carboxylic acid, I have given here the negative charge that can undergo delocalization with another oxygen atom. So I am getting this structure. And in this case, we may find the negative charge is delocalized between the two most electronegative atoms of oxygen only. But in phenoxide ion, the negative charge is delocalized between the most electronegative oxygen and less electronegative carbon. Second position, fourth position, sixth position and all occupied by the carbon atoms. But oxygen here it possesses the positive charge, but the negative charge is possessed by the less electronegative atom of carbon in the benzene ring. So in this case, the delocalization of negative charge occurs between the most electronegative oxygen atom and the less electronegative carbon atom. Moreover, in the resonance contributing structure, oxygen acquires the positive charge. But in the case of carboxylic acid, only the negative charge is present between the two oxygen atoms alone. This is the reason why carboxylic acids are much stronger than phenols. So only the point we have to write down their contributing structure, and based on resonance contributing structure we are going to discuss about how the negative charge is delocalized. The next one, how the acidic nature of carboxylic acids are influenced by the substituents. The substituents might be a minus I group or a plus I group. Plus I groups are mostly alkyl substituent. Minus I groups, that could be any electron withdrawing group. So we can consider the influence of these groups towards the acidic property. See, if phenyl is there, phenyl is C6H5. So phenyl is lesser, that is the presence of C6H5 in the carboxylic group, that decreases the acidic property of carboxylic acid, and hence you can find that increasing order, phenyl less than iodide, less than bromide, less than chloride, less than fluoride. So these are arranged according to their electronegativity. So electronegativity of these substituents goes on increasing from phenyl to trifluoromethyl. This group is trifluoromethyl. So we can find iodine, bromine, chlorine, fluorine. Here electronegativity goes on increases from iodine to fluorine. So if fluorine is present, that becomes the strong acid compared to chlorine, bromine or iodine. After that, we have the group of radicals, cyanide, nitro and trifluoromethyl. So the presence of trifluoromethyl, that makes the acid much stronger compared to nitro or even cyanide. So from this group we can identify how do they influence the acidity of carboxylic acid. Already I said acidic nature depending upon the tendency to lose the proton. How easiest you can remove the proton, that much the acid is said to be a stronger. Suppose if I have any electron withdrawing group with the carboxylate ion, electron withdrawing group that has to withdraw the electrons from the carboxylate group. So what will happen? This oxygen hydrogen bond, if at all present, see the electron density on oxygen decreases and hence the OH bond polarity increases. So this carboxylic group can readily lose the proton. So the presence of electron withdrawing group increases the polarity of OH bond and hence increases the acidic property of the carboxylic acid. At the same time, if any electron donating groups are there, see that will release the electron towards the carbonyl carbon and hence it makes the bond stronger between oxygen and hydrogen, since in turn the oxygen withdraws the electron from the carbon. So the electron density of oxygen increases and hence polarity of OH bond decreases. Therefore, electron donating group decreases the acidic property of carboxylic acid, whereas the electron withdrawing group increases the acidic nature of carboxylic acids. Let us discuss about the influence of plus I group, that is the electron donating group, to the acidic nature of carboxylic acid. Formic acid is said to be much stronger. This is why, because it has neither plus I group nor minus I group. But in the acetic acid, we may find one methyl group. That methyl group is a plus I group. What it will do? It releases the electron towards the carboxylic group and hence it destabilizes the carboxylate ion. The stability of carboxylate ion decreases as it releases the electron towards the carboxyl group and hence the acidic nature of the pKa of acetic acid will be increases, because smaller the pKa, stronger the acid. So here the presence of plus I group that increases the pKa value and hence decreases its acidic nature. So when number of alkyl group increases, the electron releasing tendency also increases. So we can say acetic acid is stronger than propionic acid, which is stronger than butyric acid. Suppose if you have any branches, what happen? All the alkyl group that increases the electron density. For example, I have written 3 methyl group, that is the alkyl group in a chain. When we write in a chain, the tendency of plus I group decreases. So this CH2 group will have more plus I effect, but this CH3 group will get less inductive effect. But in the case of the substituted one, for example, CH, CH3, COOH. In this case, both the CH3 groups are very close to the carboxylic acid. So all of them, they are releasing the electron towards the carboxylic group and hence the destabilization of carboxylate ion increased and so the polarity of the bond decreases, so the acid it goes weaker. The next one, let us find the halogen substituted carboxylic acid. Halogens, they are differing in their electronegative value. See, fluorine is most electronegative than iodine. So the presence of iodine does not influence that acidic nature of carboxylic acids that much higher because of its weak electronegativity. So we can find iodoacetic acid, it is bromoacetic acid, it is chloroacetic acid, it is fluoroacetic acid. So all the halogen, they are all belong to same family, but as they are differing in their electronegative value, so the acidic nature of this carboxylic acid that totally depends upon electronegativity of the halogen atom. So fluoroacetic acid is much stronger acid because of its very high electronegativity compared to iodo, bromo or chloro. Here we are finding only one halogen in their acid. Suppose polysubstituted halogens are present, then we can say the polysubstituted halocarboxylic acids are much stronger than monosubstituted. See that it is monofluoroacetic acid, difluoroacetic acid, trifluoroacetic acid. So trifluoroacetic acid is found to be much stronger because in this case all the 3 hydrogen atoms are replaced by 3 fluorine atom. So it is accountable for its the highest electronegativity also. That's why it increases the polarity of OH group, so that it behaves as the strongest acid. And the next thing we can identify halogen atom from the functional group where it is present, that also influence the acidic nature. Suppose the halogen atom is present very next to carboxylic acid, those are stronger. If the position of halogen gets far away from the carboxylic acid, then that acid it undergoes weaker acid. See that we can say this is 2-fluoroacetic acid because this is the carbon 1, this is the carbon 2, or we can say it is alpha fluorobutyric acid. This is beta fluorobutyric acid. This is gamma fluorobutyric acid. So what happens? The position of fluorine atom that goes far from the carboxyl group. So when the halogen atom getting far from the carboxyl group, the influence of halogen over the carboxyl group decreases, and hence the acidic property also decreases. So we may say alpha fluorobutyric acid is much stronger than beta fluorobutyric acid or gamma fluorobutyric acid. So the position of electron withdrawing group also influences the acidic nature of carboxylic acid. The next thing, let us have a general view of the strength of carboxylic acid depends upon the substituent present in carboxylic acid. See here, trifluoroacetic acid is much stronger because I have given whose pKa value is 0.23. And then trichloroacetic acid. See, after fluorine, chlorine is most electronegative and that too present thrice the time. So this becomes more acidic. And here dichloroacetic acid. After that only we are getting NO2. So number of halogen is greater, then their acidic property will also be greater. And then nitroacetic acid, this is cyanoacetic acid, here it is formic acid. So the influence of electron withdrawing groups is observed from trifluoroacetic acid to cyanoacetic acid. After that we may find formic acid, it starts. Formic acid, it has no plus I group nor minus I group. So after formic acid we can say chloropropionic acid is stronger than benzoic acid, which is then phenylacetic acid, which is then acetic acid. So after that you can write even still more number of carboxylic acids where the length of alkyl chain increases. Also we can discuss about the presence of vinyl group and phenyl group to the carboxylic acid, in which the carboxylic groups are attached to sp2 carbon atom. They are directly attached to sp2 carbon atom, so they are getting more resonating structure and the molecule is said to be stabilized through resonance, and hence the presence of phenyl and vinyl to the carboxylic group increases its acidic nature. And we can find in substituted benzoic acid, electron donating group destabilizes that carboxylate ion and hence that makes the acid weaker. But the presence of minus I group or electron withdrawing group that increases the stability of carboxylate ion and hence that acid becomes more stronger. So we can write the methoxybenzoic acid is weaker than benzoic acid, but benzoic acid is weaker than nitrobenzoic acid. Okay students, that's all the acidic property of carboxylic acid. This is one of the most important topic, just like acidity of alcohols and phenols. And here the most expected question is why phenols are less acidic than carboxylic acid. We have to give the possible reason, as well as they can ask you to arrange the increasing or decreasing order of the various carboxylic acids given, where you have to identify which group, whether plus I group or minus I group are there. Based on that, how does it influence the carboxylic, that acidic nature of carboxylic acid? Based on that, you have to arrange it in a respective order. The next one, let us discuss about the functional derivatives of carboxylic acids. In carboxylic group, either the hydrogen atom of OH or the OH group of carboxyl group that can be replaced by suitable substituents, from which we can get the functional derivatives of carboxylic acids. Those are ester acid halide, acid amide and acid anhydride. Ester COO or acid halide, COX acid amide, CONH2 acid anhydride, COO. So in this, let us find how we have to give IUPAC name for these derivatives. It is very easy to remember. If you have acid halide, then the secondary suffix of the acid halide is oil halide. This is secondary suffix. We know the primary suffix is always about that hydrocarbon nature, ane, in, ine. So the secondary suffix only we have to remember. So for acid halide, the secondary suffix is oil halide. So we can write alk plus ane plus oil halide. Alk, that is nothing but the root word. How many carbon are there? So whether it is a saturated, so alkane oil halide. See, I have taken CH3COCl. How many carbon are there? 2 carbon. So the root word is eth, ane, oil chloride. So the name of the compound is ethanoyl chloride. For benzyl, for example, C6H5COCl, this group is said to be benzoyl group. So we are giving benzyl chloride. And in the name of acid amide, here the secondary suffix of acid halide is oil halide. Similarly, the secondary suffix of amide is just amide only. So this makes the secondary suffix. So here also you have to count the number of carbon atom along with their primary suffix and secondary suffix, that makes its IUPAC name. See, so in this compound how many carbon are there? 1, 2, 3. So the root word is prop and it is saturated. There is no double bond between the alkyl. So propane amide. So the name of the compound is propane amide. Once again, for this benzamide, from benzoic acid we are getting benzamide. And acid anhydride, once again here oic anhydride you have to take for the secondary suffix. Oic acid for carboxylic acid. In case of anhydride, you have to remove acid by anhydride. So we will get oic anhydride. So how many carbon are there? You should consider both the carbonyl group with the alkyne. So how many carbon? 1, 2, 3. This side also 1, 2, 3. So mostly similar alkyl part only will be there. So we can write it is propanoic anhydride. Propane plus oic anhydride. So the name of the compound propanoic anhydride. And for this is, it is a benzoic group. This is also benzoic. So the name is benzoic anhydride. And the last one, ester. When you name the ester, you have to identify the two parts. One is alkyl part, the other one is the functional part of alkanovate. Mostly the alkyl parts are the part of alcohol and alkanovate parts are from the carboxylic acid. So here we have to find, this is methyl. So I can write it is methyl ethanoate. And in this case it is phenyl. So I can write phenyl benzoate. So one part of the alkyl group that makes its alkyl part, the other part of that ester that makes its alkanovate part. So it is methanol, this is ethanoic acid, so the name is methyl ethanoate. Here it is phenol, this is benzoic acid, so here the name is phenyl benzoate. Preparation of derivatives of carboxylic acid. Acid halide. Acid halide can be prepared from carboxylic acid either by treating with the phosphorus halides or thionyl chloride. Here thionyl chloride is taken, so this OH group is being substituted by one of the halogen atom. We are getting acid, acetyl chloride, sulfur dioxide and HCl. And moreover, all these reactions already we have discussed under the chemical properties of carboxylic acid. Once again, just we are finding the respective preparations alone. Acid anhydride, when two molecules of acids heated in presence of phosphorus pentoxide, we will get anhydride. There is a loss of water molecule between the carboxyl group. So this water molecule is being removed by the dehydrating agent phosphorus pentoxide. Acid amide, this can be prepared by various methods. So we can treat acid chloride with the ammonia in presence of a base. We may find there is a loss of HCl, so amide is formed. Or the cyanide group, when it undergoes partial hydrolysis, we will get amide. Or when the carboxylic acid is treated with ammonia, we will get the salt, ammonium salt of carboxylic acid. Upon heating, we will get amide and water. Ester. Ester we know well, it is esterification reaction where carboxylic acid with the alcohol that forms ester and water takes place in presence of sulfuric acid. And we said the sulfuric acid behaves as a dehydrating agent. Not only by esterification, we can even prepare ester from the other derivatives of carboxyl acid. For example, acetyl chloride is taken with the ethanol. This HCl can be removed, so we will get CH3 COOCH3, esters will be formed. Let us discuss about mechanism of esterification reaction. So usually esters are formed between carboxylic acid and alcohol. In this case, carboxylic acid that develops an electrophilic site and alcohol behaves as a nucleophile. So let us discuss about the stepwise mechanism of esterification reaction. So the first step is protonation of carboxylic acid. We know well esterification reaction carried out in presence of sulfuric acid. So let us take proton from sulfuric acid. In this case, the pi bond of CO group that attracts the proton of sulfuric acid, so we are getting a positive charge over the carbon. This is said to be protonated carboxylic acid. To the positive site, the incoming nucleophile alcohol that attacks. So the second step is nucleophilic attack of alcohol to electrophilic carbon. See that this oxygen, it has two lone pair, so it attracts that electrophilic site of carboxyl group. So we are getting now oxygen carries the positive charge. So the next step is transfer of proton. The proton, it gets transferred such a way that this oxygen having a positive charge withdraws its electron from the hydrogen atom. It withdraws the shared pair of electron from the hydrogen atom. So here hydrogen develops a positive charge, and this positive charged hydrogen is being attracted by the adjacent OH group, and hence we are getting this type of protonated compound. So only here the proton is transferred from the CH3OH group to adjacent OH group. So now this OH group that develops a positive charge over this. We know well the oxygen, it never be stable with positive charge. So the second step, the next step of the reaction is the removal of water from this species. So being oxygen carrying the positive charge, it withdraws its shared pair of electron from the carbon atom, and hence we are getting water. So here the subsequent transfer of one of the lone pair electron towards the carbon, it takes place, and hence the positive charge is now shifted to another oxygen atom upon the removal of water. The last step is once again oxygen carries the positive charge, so there will be a deprotonation occur, then only we will get a pi bond between the carbon and oxygen. So the last step is deprotonation of the compound. So here oxygen carries the positive charge, so it withdraws the shared pair of electron from the hydrogen. So we are getting CH3COOCH3 plus H plus. So H plus is a catalyst. So once again the H plus is regenerated at the end of the reaction. This mechanism is somewhat complicated compared to aldol reaction or dehydration or hydration of alkene and all. Here you have to remember only these things alone. The first step alone you are developing that electrophilic site. Following that the oxygen that carries the positive charge, and hence you are doing proton transfer, removal of water as well as removal of the proton. So transfer of proton takes place among the molecule itself. The last step only you are removing the proton. So better remember the steps. According to the step you have to proceed the reactions. Properties of derivatives of carboxylic acids. Let us discuss first of all the physical properties. Just a few physical properties we have to know. One, the acid chloride. The acid chloride actually that forms fumes with moisture. This is due to the release of hydrogen chloride. So it contains a halogen. That halogen slowly dissolves in water and hence the hydrogen chloride is removed in the form of fumes. And esters. Esters, they have such a pleasant smell. It is usually said to be fruity odor. So most of the fruits we may find the different characteristic smell. Those different characteristic smells are due to only the presence of the different forms of esters in their fruits. Okay, let us discuss about now the chemical properties of acid halide. First of all, this acid halide that may undergo alcoholysis, ammonolysis and hydrolysis. Hydrolysis, using water you are going to break the compound. Alcoholysis, with the alcohol the bond gets broken. Ammonolysis, with the ammonia bond gets broken. So the lysis, it means splitting. See that with the alcohol, just now I said due to the formation of HCl, when it reacts with the moisture there is the white fumes formed. It is because of HCl. So we are getting CH3COOH, carboxylic acids are formed. But actually acid halides are insoluble in water, but slowly it dissolves in water and hence it releases the HCl. With the alcohol, when you have alcohol, this HCl will be removed, so we are getting ester. So the first case we are getting acid, the other case we are getting ester with alcohol. In place of alcohol, if we take ammonia, then there is the formation of amide. Amide is formed. So in all the cases we may find there is a release of hydrogen chloride. The next reaction, reduction. The COCl group that can be reduced to either primary alcohol or even aldehyde. If you want to get aldehyde, then the reaction is Rosenmund reduction, where we will take palladium barium sulfate. So the COCl group is reduced to aldehyde. But in presence of lithium aluminum hydride, it goes to primary alcohol. So even in the previous case, in the absence of barium sulfate, it usually gives primary alcohol. But we need to stop the reaction up to the formation of aldehyde. That's why palladium is coated with barium sulfate we are taking as a reducing agent. Then with the primary and secondary amines, amines functional group NH2. So this is when only one alkyl group is present, then that amide is said to be primary amine. Or if two alkyl groups are present, that is called secondary amines. See, two alkyl groups are present, that is said to be secondary amines. So acid halide, just like ammonia, the reaction with the ammonia, it may also react with the primary amine and secondary amine. Correspondingly, the HCl will be removed. So we are getting alkyl substituted amides are formed. With the ammonia, it forms only the amide, but with the primary and secondary amine, it forms alkyl substituted amide. So it is N-alkyl acetamide. This is N, N dialkyl acetamide. That's all the chemical properties of acid chlorides. The next one, chemical properties of acid anhydride. See, first of all, acetic anhydride that gets hydrolyzed by water. So there is formation of this water molecule that can break this like this. So we are getting CH3COOH, CH3COOH. So we are getting two molecules of acetic acid. The next reaction with the alcohol. When anhydride is treated with the alcohol, we will get a carboxylic acid and ester. So the alcohol that may split that anhydride linkage, carbon oxygen linkage and CO linkage. So we are getting C2H5 over here and OH. So we will get CH3COO C2H5 plus CH3COOH. So here the cleavage takes place between the acyl part and this carboxylate part. With the ammonia, ammonia also split the compound the similar way. Here carboxylate part and acyl part gets broken. To the carboxylate part, hydrogen is being shared. With the acyl part, NH2 group is shared. So we are getting acid and acid amide. Amide and carboxylic acids are formed with the PCl5. This PCl5, it has 5 halogen atoms, so the bond it gets broken like this. So both of the acyl part takes away the halogen atom of PCl5 and the PCl3 with the oxygen that forms POCl3. So we are getting 2 molecules of ethanyl chloride with phosphorus oxychloride. That's all the chemical properties of acid anhydride. The next chemical property, let us discuss for esters. Esters usually upon hydrolysis we know once again it will give rise to carboxylic acid and alcohol. So the next one is transesterification. This transesterification is one form of the ester is converted into another form of the ester. So the alkyl part of the ester that can be even lowered with the alkyl group or even higher with the alkyl group depends on what kind of alcohol we have taken. So in this case I have taken ethyl ethanovate. It is converted now methyl ethanovate. So the ethyl part is changed into methyl part. So one of the alkyl part is changed with another alkyl part but forms the ester is known as transesterification reaction, and this is also carried out in presence of an acid. So this methanol it can split the bond over here. So we will get here we are getting the hydrogen here OCH3 group attacks. So we are getting CH3COOCH3 plus C2H5OH. With the ammonia, once again amide and alcohol will be formed. So here the bond it gets broken between the acyl part and alkoxy part. To the acyl part NH2 is getting shared and to the alkoxy hydrogen is shared. So we are getting alcohol with amide. Then with the phosphorus pentachloride, same way we will get the splitting of acyl and alkoxy. Here one halogen will be there, and this case we will get another halogen and this oxygen with the PCl5 that makes POCl3. So two of the halogen that shares with the acyl part and alkyl part, and one more PCl3 group with the oxygen that makes POCl3 compound. Claisen condensation reaction. In this we can able to prepare beta keto ester. So here the reaction condition is the ester should possess at least one alpha hydrogen atom. So where the ester contains the alpha hydrogen will undergo Claisen condensation reaction in presence of the base C2H5ONa, sodium ethoxide. So in presence of base, here the same ester it may undergo self condensation reaction. So I have taken ethyl ethanovate with ethyl ethanovate. So the first form of ethyl ethanovate is condensed with the methyl form of another ethyl ethanovate. So what I may get, this CH3CH2OH will be removed as alcohol. So I can have CH3CO, CH2COO, C2H5. See here I have the ester part as well as a keto part. And this keto, this is the functional group, it is alpha carbon, this is the beta carbon. So the ketonic carbon it becomes beta carbon. That's why the name is given beta keto ester. That's all the chemical properties of esters. The last topic of this chapter is chemical properties of acid amide. So the first one is amphoteric nature of acid amide. What do you mean by amphoteric nature? Amphoteric, that means the substance which is able to react with both acids and bases are said to be amphoteric in nature. So this amine it has that basic nature. Amine it has a basic nature. So it may undergo reaction with the acid or even with the base. When it undergoes reaction with the acid, you may find the formation of NH3 and CH3COCl. Acid chloride is formed. Or with strong electropositive metal just like sodium, one of the hydrogen is being substituted by the metal. So there is a release of hydrogen with sodium acetamide. This is said to be, it reacts with the acid. Even in place of sodium, we can take sodium hydroxide also. When we have sodium hydroxide, this one of the hydrogen combined with the OH, so that forms water along with the same sodium acetamide. So this first reaction, it can react even with directly to acid, or it may be hydrolyzed by water in presence of acid. Whatever be the reaction, with the hydrochloric acid, it forms acid chloride, but with the water in presence of acid, it forms carboxylic acid. So, this reaction that can be taken for amphoteric nature of amide, or even you can consider acid hydrolysis as well as alkaline hydrolysis of amide. The next one, dehydration reaction. So, in dehydration reaction, when amide is strongly heated with the phosphorus pentoxide, a dehydrating agent, there is a loss of water molecule between the carbonyl group and the amine group. This carbon and nitrogen get a triple bond. So, nitriles are formed. Upon the dehydration, we are getting nitriles. Reduction, the CO group is converted into CH2 group. So, amides are reduced to amines. So, we are getting ethane amine. So, amines are formed by the reduction of amide. The last one, Hoffman degradation reaction. Degradation means when you compare the number of carbon with the product and that of the reactant, you may find decrease of one carbon. That's why the reaction is said to be degradation reaction, in which the amides are converted into primary amines, and here the reagents are bromine with the potassium hydroxide, where this KBr is removed as potassium bromide, and the CO group with the KOH, it is removed as potassium carbonate. It has 2 bromine atoms, so let us take KBr 2 times. So 2 potassium with the 2 potassium 4 times. So potassium hydroxide is taken as 4 times. So out of this 4 OH as well as the 2 hydrogen, out of the 4 hydroxide group, we will get 2 molecules of water. So total number of oxygen 4 plus 1 5, here 3 plus 2 5. So now you may find the amide is converted into amine. CH3NH2 is formed. In addition to the formation of primary amine, the rest of the byproducts are potassium bromide, potassium carbonate and water. Okay students, that's all. This chapter got over. We discussed several topics from this chapter, and we are going to start the next chapter from the same organic chemistry. Until then, bye bye.